Hi, this is a small tutorial on the basics and implementation of B plus trees. trees. So basically B plus tree is a type of tree which represents sorted data in a way that allows efficient insertion, retrieval as well as removal of records. So what we use is a key for each node here. It is a dynamic multi-level index with maximum and minimum bounds on the number of keys in each index segment. And in contrast to a B tree, all records in a B plus tree are stored in the leaf level of the tree, and only keys are stored in the interior nodes. Basic database management systems like CouchDB, Tokyo Cabinet support this kind of tree for data access. This slide gives an insight of the history of B plus trees. You can just have a reading of the slide. These are the characteristics of B plus trees. Here, the data records are stored only in the leaves, and internal nodes just store just keys, as I mentioned before. The keys are used for directing a search to the proper leaf. In case a target key is less than a key in an internal node, then the pointer just to its left is followed. If the target key is greater or equal to the key, then the pointer to its right is followed. We see that a B plus tree combines features of ISAM and B trees. Here we see the concepts used in B plus trees, that is a sequence set and an index set. So in a sequence set, each node in a sequence has a minimum of n by 2 elements and a maximum of n elements. And properties of index set include that each node in an index set should have a minimum of m by 2 and a maximum of m elements. If a node has I elements, then the node has I plus 1 child nodes. The root node shall always have a minimum of 1 element, that is 2 child nodes. These are the rules that are defined for an efficient creation of a B plus tree. It is actually a 3-step approach that you can see in the slide. This explains a basic B plus tree structure which has 2 levels. It consists of an internal node, a child pointer, a search key value, a leaf node, sibling pointer, data pointer, and key value as mentioned in the slide. Let's go to an example as to how a B plus tree is created. We take the input keys as follows. Since it is a B plus tree of an order 4, so we take the first 4 keys and insert them in alphabetical order. Next step is to insert T, which is the next key. While inserting T, since B plus tree of an order 4, the initial node is full. Therefore, we split the node and promote the lowest element from each node to the parent node. As we see, T is being inserted. Next, to make the first element invisible in the index node. Next step is to insert the key Y. We see that the Y is greater than separator R, so it has to go to the right node. Next we see the branches coming up and the B plus trees. And next node to be inserted is U, as the right child node is already full since it's an order 4, so we again split it. So we see the splitted nodes EQ and RT, and we insert U. Next we see the branchings coming up. Next node to be inserted is I. The space in the nodes, so we directly insert I into the appropriate node, and we see the branches. Then next key is O. The nodes coming up, and O is again inserted to the appropriate node, and we again see the branchings. Next key is P. So P has to be inserted in the left child node. As it is full, we again split the nodes into EI and OQ. P of course goes to the OQ node, and the other nodes remain unchanged. E still remains the invisible element and the branches. Next element is A. So here again, no need to split the nodes. We can insert A into the first node itself. Here we see A coming into the node. Now A becomes the invisible element as it is the lowest element in the first child node. Again the branches. Next key is S. Here again no partition is required. The nodes remains unchanged from the previous step, and we directly insert S in the RTU node, and we branch it. Next key to be inserted is D. D again has to be directly inserted without any split. It can be directly inserted into the node containing AEI, and we can directly branch it to the parent node. Next key to be inserted is F. From the previous slide we see that the left child node is already full, and so is the parent node. So here we split both the parent node as well as the left child node. The left child node is split into the AD node and the EI node. Next we accommodate F. Next, since the parent node is full, we split that too. So the AE node and ORW node comes to existence. Next is the other nodes remain unchanged. We branch those with the parent nodes. Now we see the change in the invisible elements too. So in the 0th level, the A key becomes the invisible element, and in the first level, A and O are the invisible elements. Yeah, so next key to be inserted is G. Now again we see that the same rules have been applied for the proceeding to the creation of a B plus tree. So the following slides will explain the same idea as to how to construct the B plus tree. Next key is H. So here we split the EFGI node into the EF and GI node separately. Then we insert H. Other nodes remain same. Next key is J. No need to split any nodes. We directly insert into one of the nodes, and the other nodes remain unchanged. In order to insert K, we split the node JHIJ equally. Next we insert K, and the other nodes undergo no change. Yeah, so L again has to be directly inserted as we see in the video. Next key is Z. We again directly insert it. Now next key is X. We again insert it to the appropriate node. Next we insert C into the node containing A and D. Again no changes to the other nodes. Next node to be inserted is V. We split the RSTU node to insert V. Then we insert the element. The other nodes remain unchanged. For inserting key B, no splitting required, direct insertion is done. Next node to be inserted is N. We split the node containing I, J, K, L keys. We insert N into the appropriate node. The other nodes remain unchanged. Next node is again M. Next key is M. Here we insert it directly. Now we finish the creation of the B plus tree. Now on the previous slide we see the invisible elements. In level 0 it was A, and in level 1 it was A, I and O, which were represented in italics. So now the final B plus tree is created without the invisible elements, and this is how the final B plus tree comes up. Now I'll brief about the deletion of a key from a B plus tree. The algorithm is as follows. The rules are given here. The main two concepts applied here are merging and redistribution. This explains the concepts of merging and redistribution. We see that merging is a process where the elements of a node are merged with its siblings, provided that the sibling has at least one element less than the order of the sequence set. Redistribution goes as follows. It is a process of rearranging the elements of a node with its sibling. If we go through the merging section, now consider a B plus tree given as follows, where A is the invisible element as seen in the parent node. It's given in italics. So in case F has to be deleted, node 1 deleted, in this case we merge node 1 and 2. So the final result comes as follows. This explains the redistribution section. Again we consider the B plus tree where A is again the invisible element. Now in case we need to delete F, the redistribution of node 2 and 3 is done as follows. So this basically gives an overview of a B plus tree. So the order of branching factor, which is taken as small case b for a B plus tree, measures the capacity of nodes. So if the B plus tree is of order 7, so the internal node will have children ranging from 4 to 7, and the root node will have children ranging from 2 to 7. These are the references I've used for the presentation. Thank you for watching the video.